Dear students, welcome back. In the previous lecture, we had seen about kth order linear ordinary differential equations. That is, you have a differential operator L of kth order, and we said that if it's so when we say linear, we basically mean it's of the form it's of the following form, where k is from I should say again, if I had to say it's kth order, let's make this I runs from 0 to k. Okay, so we have seen that any kth order linear ODE, and if you are looking at the equation of this form, then we have seen that its solution space, which is the null space of this operator L, this is k dimensional. Right? This is k dimensional, is what we have seen in the previous lectures. So in this lecture today, we are going to find out how to find the k linearly independent solutions of the solution space, which is the null space, for the special case when these coefficients are constants. That is, these ak's are constants, so they are independent of x, right? So they are all constant functions, k different or k plus 1 different constants, right? So in other words, so we are going to look at linear homogeneous, so homogeneous because 0, so linear homogeneous equations which are of constant coefficients. So you have ak, dk, so on up to a1 d by dx plus a0. Okay, we are going to look at how to find solutions for this type of linear homogeneous constant coefficients differential equations. Okay. Okay. So we have a linear. So we have a linear, right? This is linear in Y, homogeneous, right? F is 0, kth order, okay, ODE with constant coefficients, which means these AIs are all constant. So if you are given an ODE of this form, then what is it? And we already know from the previous lecture's result that the solution space should be k dimension, which means there are k linearly independent solutions. So what are the k linearly independent solutions for a linear homogeneous constant coefficient differential equation? This theorem tells you about that. So what is the statement of the theorem? It tells you that if you are given the ODE, which is linear homogeneous constant coefficient, then there is a corresponding equation, algebraic equation, which is called the characteristic equation, which is a kth degree polynomial. Right? There is a corresponding algebraic equations where what you have done, you have replaced all the derivatives with powers of n. So here you treat m as the unknown variable here. So here y is the unknown, right? So here you treat m as the unknown variable. You have a k degree polynomial here. It's an algebraic equation, right? So corresponding to a kth order differential equation, linear differential equation, you have a kth degree polynomial which you call the characteristic equation. So the solution of, so solving this ODE depends on solving this algebraic equation, and you already know solving algebraic equation is not always an easy thing to do, right? You probably know up to cubic and some cases quartic and so on, right? So if you solve algebraic equations, then using the roots of this algebraic equation, you can characterize the solutions of the differential equation. That is what this theorem tells you. So what are the different cases? So you look at this algebraic equation. This is of kth degree, which means we know from the fundamental theorem of algebra that they should admit at most k roots, right? They should at most k roots. So if those roots are k distinct real roots, so let's call it m1, m2, m3 up to mk. So this algebraic equation, which is called the characteristic equation, admits k distinct real roots, then which means you have m solutions to this algebraic equation. Then the corresponding solution to this differential equation is the linear combination of exponential of mix, where mi's are the roots of this algebraic equation. That is the general solution of this ODE. So as I said, this is a kth degree, kth order ODE, which means it should have k linearly independent solution. What is this theorem telling you is that if you have roots m1, m2, so on up to mk, okay, if you have k roots to this ODE, then you have e power m1x, e power m2x, so on, e power m3x. These are the k linearly independent solution. So the linear combination of this should be the, right? So the linear combination of this k elements should generate the solution space of this, and which is this. So y is a linear combination of these k elements. Okay, that is what the first statement tells you. And this is a case where this m1, m2, sorry, this is mk, right? m1, m2, mk, they are all distinct in that situation. Okay, we will see how we got this. Okay, we will see a proof, at least give you the idea behind how you obtain this relation from this from this algebra. I mean, from the roots of the algebraic equation. How do you go to this, right? I'm going to explain the idea behind it, but for time being, the statement. So this is the first statement. Similarly, the second statement is that, so in some cases it can happen that not all the real roots are distinct. Some of the roots could be repeated and the rest of them are distinct, right? So in m1, m2, m3 up to mk, some of the mi's might be same, which is called the repeated roots, right? You have seen this even in quadratic equation and so on. You can have repeated roots. So in those cases, when you write, and for those repeated roots, let's say m1 or n, let's say e power mx and e power m2x, and if m1 and m2 are repeated roots, then they are same, which means these two are not linearly independent. So this argument is not true, because for repeated roots, they will no longer be linearly independent functions. So you don't actually have k linearly independent functions here, right? But we said this is a k dimensional space, I mean a solution space. So in those cases, something else happens, right? So when you have repeated roots, so the repeated part So here we are assuming m is the repeated root. Okay, so you have L repeated roots of, so m is the repeated root which is repeating L times, and if that is the case, then let's say m, so you have m, so this you can think of as 1 dot, right, 1 dot m, right, 1 multiplied by m, so 1 dot m, then you take e power mx, you take x. We have already seen that 1 x, x square, x cube, and so on, these are all linearly independent, right? So if you have m as a repeated root, you already know e power mx is one possible candidate. So since it's repeating L times, you cannot, e power mx is not linearly independent with itself. So to obtain a linearly independent function corresponding to e power mx, you choose x emx. Since you have L repeated roots, you need to do this, and since this is k dimensional, so you should have L linearly independent to start with, so that when you mix with the rest of the distinct roots here, you will have totally k linearly independent solutions. So you take m, you take x e power x, do this up to, so 1 to L minus 1, right, L minus 1 emx. So you see, that's what we have done here. So this first thing is a linear combination of these L elements, right? So you have L elements here. So these L elements gives you one linear combination. The remaining L minus k elements comes from the distinct roots, the way we have done here. So totally you have, this is the linear combination. This is the linear combination of k linearly independent functions. What are the k linearly independent functions? All the distinct roots gives you e mix, and all the repeated roots gives you this. Okay, so that is the general solution of this ODE in the case when some of the roots of this algebraic equations are repeated. Okay, and these are all real roots so far. So you have seen distinct real root situation, you have seen repeated real root situation. Now what about non-repeated pair of complex roots, right? So you have seen that algebraic equations can also have complex roots, right? So you can have situations where in this algebraic equations you have complex roots, and you know that complex roots appear in pairs, right? So when you have non-repeated pair of complex roots, and like some of them are non-repeated pair of complex roots and some of them are distinct, some of them could be repeated real roots, right? So whenever you have distinct real roots, you use this expression for those repeated for those distinct real roots. Whenever you have repeated real roots, you use the idea explained here for repeated real roots. So you can have all possible situations. So if you are having distinct roots, then you use this. If you have repeated real roots here, you use this situation. Now what we are saying, suppose some of the roots are non-repeated complex roots, then what happens? So in that case, what are the roots? I mean, what is the corresponding thing? So if you have, let's say we have one non-repeated pair of complex root, okay? So I'm just explaining that situation. So let's call the root as, it's a complex number, so it's a plus ib, and then it will occur in pair. So it's a plus ib and it's conjugate a minus ib. So in that situation, exponential of the real part of x and then linear combination of, there's alpha 1 sine bx and alpha 2 cos bx. we will show how this expression becomes this. It's not difficult. I'm going to do it in a proof with examples and so on. You will understand this better as we do examples and proof. But the idea to remember here is that distinct real roots, you have this expression very similar to here, right? What we have assumed is, so we have just assumed that the first two roots are complex, but it could be appearing anywhere. Don't bother. You can always rearrange such that the non-repeated pair of complex roots are m1, m2. So let's say if m1 and m2 are precisely these, that is conjugate, m1 is a plus ib, m2 is a minus ib, then that gives you this expression and linear combination. So alpha 1, alpha 2 is appearing here and the rest of them for distinct roots. If in this situation you also had repeated real roots, you add in those corresponding terms. Okay, so that is the general solution for a non-repeated pair of complex roots. What happens if you have a repeated pair of complex roots? So let's say you have L repeated pair of complex roots, right? In that case, very similar to what we did here, if you have repeated roots, then they are same functions. So you have to choose appropriate linear independent function. So you use the same idea of multiplying by the polynomial of, some degree of x has to be multiplied to make it linearly independent. So that's what we do here. So it's a repeated pair of L roots. So the real part A appears like here as e power ax, and the imaginary part B appears as sine B and cos B. It's linear combination of that, right? But now since they are repeated roots, L repeated roots, you have a linear combination up to L minus 1. That is x power 1. So I equal to 1 means x power 0, which is this situation. Then you multiply by x here. Then you multiply by x square. So you do this up to L so that you get L linearly independent functions. And the remaining, as I said, the corresponding part. So remaining you could have distinct real roots, you could have repeated real roots, you could have non-repeated complex roots. Depending on that, you add the corresponding solutions. Okay, so these are the 4 situations that can occur for this algebraic equation. So you see what this theorem has done. This theorem has reduced solving an differential equation, which is a linear homogeneous constant coefficient differential equation, a special case. Solving that is reduced to the solving an algebraic equation, right? So you just solve an algebraic equation, and depending on the roots of the algebraic equation, you can write down the general solution of the differential equation. Okay, so we will understand this with proof and example. So so we have 4 situations. We will do these 4 situations: distinct real roots, repeated real roots, distinct complex pair of roots, repeated complex pair of roots. Okay, 4 situations we will do with proof and examples. So let's do the proof of distinct real roots. So what is distinct real roots situation? So what is the ODE that you have, if you recall? So it's a constant coefficient linear ODE, y power k and so on, a2 y double prime, a1 y prime plus a0 y equal to 0, right? So you have, this is the kth order constant coefficient linear ODE. It is the kind of ODE that you are given. And what did we say is the corresponding algebraic equation? So the corresponding algebraic equation is a power k, m power k and so on, a2 m square a1m plus a0 equal to 0. Okay, now, and we said, so let's look at this case. I mean, just start with a simple case. Let's take when k is equal to 1, let's say, because when k is equal to 0, it's not even a differential equation, it is just some scalar multiple, right? So the first order differential equation, which is when k equal to 1, is precisely a1 y1 y prime plus a naught y equal to 0. So we want to solve, let's say we want to solve this. So what we are looking for is a function unknown y which has this property, I mean which satisfies this equation. What is this equation? This equation is same as y prime equal to minus a naught a1 y, right? This is this equation. And what is this equation is telling you? That you are looking for a function y such that after you differentiate the function, so you're looking for a y such that when you differentiate y, that is when you compute y prime, it is some scalar, some number times the function itself, right? That's the form here. And do you know any function which has this property? You do, right? You know that if y is exponential of alpha x, then y prime is alpha times exponential of alpha x, which is alpha times y. Right? So if you are looking for a function y which is just a scalar multiple of, I mean whose derivative is scalar multiple of itself, then you know that one such function is exponential. In fact, you know by fundamental theorem of calculus that the only possible functions are exponential of that scalar function, right? So you know such functions. So when you say you want to solve a function here, one can, without laws of generality, can expect or guess that a possible solution to this ODE should be exponential, some linear combination of exponential of some constant times x, right? Because exponential is the one that has this property, and this is what being extended when we say the linear case. Okay, so that's what we are saying here. So observe that the derivative of exponential is constant multiple of itself, and that's the kind of ODE that you're starting with. That is, when you look at a linear homogeneous ODE, it is like you, after differentiating, what you're getting is a scalar multiple of previous derivatives and so on, right? So such property is you observe for exponential. That is, if you take the kth derivative of exponential of some cx, then you get the k power of c times the same function. So it is natural to expect the solution of constant coefficients linear ODE in the form of exponential. Okay, so let's say that the solution y that you're looking for is of the form e power mx. It's just that we don't know what the m is, right? If we find the right m, then we have found y, right? So let's say our solution to the ODE that is given to us, which is the linear homogeneous ODE. So the solution is of the form e power mx, okay, where m is to be determined appropriately. Once you determine m, you have determined y. So if you use this information in the ODE, right, in that linear ODE, then you get an equation of this form, right? For instance, in the first order situation, I told you if it's a1 plus a0 y equal to 0, then if you use this information that y is e power mx, then y prime is e power mx m a1 plus a0 e power mx, and that is precisely e power mx comes out, which is a1 m plus a0 m, and that was equal to 0. So you see, you started with this ODE. When you assume this form of solution, then that ODE becomes this. So where that y form has come out, and what you are left with is a polynomial of degree 1 in the case of first order. If you start with a kth order, you would have a polynomial in M of degree k, right? So that's what you will get here. That's what you get here. So if you substitute this information in the ODE, then you get e power mx times a polynomial of degree k. Now you see this multiplied by, so this multiplied by e power mx is equal to 0. Exponential is never 0, which means if this equation has to be valid, then this algebraic equation here should be equal to 0, which means the m that you're looking for, so m should be chosen such that they are the roots of this algebraic equation, and that's what was the statement of the theorem, right? So m should be the roots of this algebraic equation. Now once you choose m as roots of this algebraic equation, so how many, as we know from the fundamental theorem of algebra, that if you have a k degree polynomial, then it at most kind of admits k roots. Okay, so the possible choices of m are the roots of the k degree polynomial. So once you have the k roots, which means e power m1x, e power m2x are k different functions, and these k different functions are linearly independent, so their linear combination will be the general solution. That was the first item of the previous theorem, right, which is the distinct real root case. And how do you check that those for k distinct roots they are linearly independent? You can use the Wronskian. Okay, so you have k functions which are all exponential. So it's e power m1x, e power m2x, so on up to e power mkx. You have these k functions. So you compute its Wronskian. You will see that it is non-zero. So they are linearly independent functions, and hence the linear combination of these linearly independent functions should be the solution of the kth order ODE, because the solution space is of k dimension. Okay, so that's the proof of the first part. So let's look at an example. So you have taken a second order ODE which is linear. They have constant coefficients, right? In this case 1, -3 and 2. So you have constant coefficient linear ODE. So what is that? So to find all the solutions of this differential equation, what should you do? First you have to look at the corresponding characteristic equation, which is a polynomial of degree 2 in this case. So what is the corresponding characteristic equation? Characteristic equation is m square minus 3m, right? So second order, this becomes m square m, and this is degree 0, 0. So you have this, and this is a cubic equation which you can solve. So they have two roots, m1, m2, there's 1 and 2, and they are distinct roots. m1 is not equal to m2. So once you have found m1, m2, we observe that they are real and distinct, which means you look at the corresponding solutions, e power m1x, which is e power x, e power m2x, which is e power 2x, right? So you have two functions now, and the theorem tells you that these two should be linearly independent. You can verify that by Wronskian. So you look at the Wronskian of these two functions. So e power x, its derivative, e power 2x, its derivative, it is e power 3x, which is non-zero for all x, right? Whatever the domain that you had originally here. So this differential equation is given in some interval I, right? So this x is coming from that interval I. So whatever that I is, this is valid. So it's linearly independent, which means the solution of the second order ODE is a linear combination of these two functions, which is this. So it's linear combination of these two functions, alpha 1 times e power x plus alpha 2 times e power x, for every choice of alpha 1 and alpha 2. That is, alpha and alpha 2 are real numbers or some number, real numbers, any real number. So for every choice of alpha 1 alpha 2 is a solution. So the number of solutions is infinite, right? You see, but it's of dimension 2. So just by knowing e power x, e power 2x, so any solution is linear combination of this for some alpha 1 and alpha 2. So we have solved this ODE. So you see, it's simple. Okay, it's in the case of real and distinct roots for the characteristic equation, or this is also called auxiliary equation in some. I mean, they are interchangeably used. Okay, so characteristic equation or auxiliary equation. Okay. Now let's look at another example. In this case, we have taken a third order ODE. Okay, so but they are all constant coefficients. So what do? You look at the corresponding characteristic equation, which is a cubic equation in this case, right? So if you have a cubic equation, so if you solve for the roots of this cubic equation, now again you have to use the known tricks of solving a quadratic equation, cubic equation, and so on, right? So if you solve for this cubic equation, which is now an algebraic equation, you should get three roots. So you have the roots as -1, 2, and 3. So you have, and they are all distinct roots, right? So m1, m2, m3 are all distinct. So you have three distinct roots. So the corresponding functions are exponential of these three, which is e power -x, e power 2x, and e power 3x. Okay, we need to check that they are linearly independent. Please do it as an exercise. So look at the Wronskian and show that it's non-zero, so they should be linearly independent. And since they are linearly independent, any general solution of this should be the linear combination of these three functions. Okay, so we have solved. Right. Similarly, you can do this for any case when you have distinct real roots. Now let's come to the second case when you have repeated real roots. So what if some of the roots are repeated? So what happens when you have a repeated real root? You have a root m of the characteristic equation of the algebraic equation, which is a repeated root. Let's say, so we say start with, so let's say it's repeated twice. Then the corresponding solution is e power mx. It's just that now you cannot look at e power mx twice and then you cannot say that e power mx is linearly independent with itself, right? Right, so these two are not linearly independent, right? So what you do is that you are given a e power mx, you look for a linearly independent function e power mx times v for some suitable v, and that v I have already told you how to choose. Since we see this as 1 times e power mx, a possible linearly independent thing is, see, I could have for 1 x square, I mean these are all linearly independent. So once I start with 1, I could also choose x square, right? But then to keep things simple, not to increase order and so on. So if you have this set, so the possible next higher degree linear independence is x, if you're looking for a linearly independent function for the set 1 comma x, then the choice should be to add x square. Now if you're looking for a linearly independent set for this, then the possible next choice is to add x cube and so on, right? So in this case you are given e power, so e power mx is the first choice. So now what you do, you choose a linearly independent solution. So you choose x e power mx. This you can verify immediately using your Wronskian that they are linearly independent. Okay, so now that you have since we have assumed twice, so we can just stop at 2. If you had L, you go up to xl minus 1. Okay, so if you have L repeated roots, you go up to xl minus 1 to choose L linearly independent solution. Okay, that's the idea for repeated roots. So now you will have, and for let's say if you have 3 repeated roots, you go for 1 multiplied by e power mx, x e power mx, x square, and so on. As I said, you go up to L minus 1 in case of L. You go up to L minus 1. Then the general solution would be linear combination of all the linearly independent solutions. So as an example, let's take this ODE, which is a constant coefficient ODE. What is the corresponding characteristic equation? The characteristic equation is m square minus 6m plus 9, right? If you solve this quadratic equation, you are going to get 2 repeated roots. So this is a second order ODE, and for second order ODE you have 2 repeated roots. So the corresponding solution is e power 3x, but since 3 is repeated, so the solution space of this cannot be generated by e power 3x, right? Because they are not linearly independent. So what you do, you choose a linearly independent corresponding to this, which is x e power 3x. Okay, so the corresponding solution is e power 3x. You choose x e power 3x as the other solution, and in that case your general solution is linear combination of these two, x e power 3x and x e power 3x, which is this. Okay, so in the case of repeated roots, this is the general. This is now 2 dimensions. Okay, that is what you do. Now let's look at another example in the case of cubic equation. So I'm just trying to give you some different example where you have different situations so that you understand better. So you have a cubic equation. What you do, you first write down the corresponding characteristic equation, which is you have a third degree equation, so you have the corresponding cubic equation as the characteristic equation. If you solve for this cubic equation, as I said, solving for quadratic equation, cubic equation is, you should employ methods which you already know from your school. So if you solve for this cubic equation, what you get is 2 repeated roots and 1 distinct root, right? So you have 3 roots, but 2 of them are repeated. So the choices that you have is e power 3x and e power 2x. These two are linearly independent, you can verify that, but this is third degree, so you need one more, so the solution space of this should be 3 dimension, so you need one more linearly independent function. So that's because, and you don't get one more because 3 is being repeated. So what you do, you put a linearly independent solution corresponding to this, which is x 3 e power x. So 2 of the roots are repeated. So the corresponding solution is e power 3x, e power minus 2x. So the general solution is you add this linearly independent solution to e power 3x, which is the repeated root. So then the linear combination of that is the general solution. Okay, right. Easy to do. So we have seen the 2 situations. Now the third situation is when you have a distinct pair of okay, I have one more example with, just to give you another dimension. So you have 4th order ODE which means now you are going to get a characteristic equation which is fourth degree polynomial, which is this. And in this case, if you solve this fourth degree polynomial, you are going to get 4 roots, of which 3 of them are repeated and 1 is a distinct root. So the corresponding functions are e power 2x and e power minus x, but you need 4 of them, and what is repeated is 2. So corresponding to e power 2x, you put x e power 2x and then one more, which is x square e power 2x, because you need total 4. Now you have 4 linearly independent. So some roots are repeated, which is 3 roots are repeated. So you add x e power 2x, x square e power 2x, and linear combination of that. Okay, so this is how you do for any situation where you have repeated real roots. So I have kind of shown you different order ODE and different types of repeatedness, right? And you have repeating twice, repeating thrice, and so on. So this is the idea that you employ for any general situation. Now let's look at the third type, which is the case where you have a conjugate pair of complex roots which are not repeated, right? So when you have a plus ib, a minus ib as the possible m, which are the roots of the characteristic or the algebraic equation, right? A plus ib, a plus or minus ib. So in that case, what did we say? The corresponding solution is exponential of m power x, right? Which means exponential, so e power m, but now m is complex. Whereas what we are looking for, so these are all complex solutions of the differential equation, because m is complex. So what you have is exponential of m, which is exponential of a plus ibx, which is this, or exponential of a minus ibx, which is this, right? So these are the possible solutions, right? But you already see this is a complex value thing. So these are complex solutions of the ODE, whereas we are looking for real solutions, right? So from this complex solution you can obtain, but these complex solutions are linear combinations of some real solutions, right? Basically you can think of them as linear combination or the complex linear combination of exponential of cos b, exponential ax cos bx, and exponential ax sin bx. These both these are linear combination of exponential ax cos bx, exponential a sin bx, right? So since we are looking for linearly independent solution, we can think of these complex solutions as linear combination of exponential ax cos bx and exponential ax cos bx. So these are real functions, and these complex solutions are obtained as linear combination of these real solutions. Okay, so that is how we get this. So which means for the complex conjugate pair, it should be linear combinations of these functions. So if you take that, so whenever you have a conjugate pair of non-repeated complex root, the corresponding part of the general solution should be replaced by e power ax, linear combination of that, which is linear combination of these two, which is alpha 1 times of this, alpha 2 times of this, which is this. Then depending on the other roots, whether they are real, distinct, whether they are repeated real, you appropriately add the other parts of the solutions. Okay, so then you get the full general solution. Okay, so let's look at some examples to understand this. So this is, if you remember the earlier examples, we had shown how sine and cos are the solutions to the second order ODE. Now we are actually proving that situation here. So you have a second order constant coefficient ODE. let's look at the algebraic equation, the characteristic equation corresponding to it, which is m square plus 1. You already know m square plus 1, which is a quadratic equation, and if you solve it, you are going to get complex roots I and minus I. They are conjugate pair of roots, right? So the corresponding solutions are, as I said, for m1. So in this case, the real part is 0, the imaginary part is plus or minus 1, right? So general solution is e power a. So in this case, your a plus or minus ib, your a is 0, your b is plus or your b is 1, right? So exponential of 0x alpha 1 sine bx, which is sine x, alpha 2 cos bx, which is cos x. This is precisely what you have here. So in this case, you only have complex roots, so that's just a linear combination of these two, which is why we have already used this information that so the general solution, even in an exercise or in some assignment problem, we have said we will see later in the lecture that these are the only possible solutions. That is, the linear combination of sine and cos are the only possible solutions of this ODE. Okay, so this is the general solution of the second order ODE. Let's look at this another example, which is a second order constant coefficient ODE. So the corresponding characteristic equation will be a quadratic equation, m square minus 6m plus 25. And if you look at the two roots, they are complex conjugate roots, 3 plus or minus I4. So in this case, a is 3, b is 4. So you look at the corresponding solution, e power 3x, alpha 1 times sine 4x and cos alpha 2 times cos 4x. So that's the general solution for this second order ODE. Let's look at this fourth order differential equation. Okay. So if you write down the corresponding characteristic equation, you have a fourth degree polynomial. You solve for the roots here. So you are going to get 4 roots. 2 of them are repeated roots. Not repeated roots. There are 2 pairs of non-repeated complex roots. Okay. So 1 plus or minus 1 plus or minus I2, but there are 2 roots of 1 plus I2 and 1 minus I2. Okay, so there's repeated roots. So what do you do? So in this case, the complex roots are repeated. Okay, we are in the next situation. Complex roots are repeated. So what you do? You have one. So you have one. So you have one pair. So 1 plus or minus I2 is the pair. Is a complex pair, and this is repeated. So corresponding to this, you have e power ax, in this case e power x, alpha 1 sine 2x plus alpha 2 cos 2x, right? But even for this, you will get the same thing. But then that's because of repeated, right? But then they are not linearly independent, because for this also you have the same expression. So you need to choose a linearly independent solution corresponding to this. So what you do, you choose the same e power ix, but so for this you choose a is 1, so you choose e power ax. Here you need to, let's say in this case beta or something, some other scalar, right? Whatever it is, but you need to multiply by x. So you say beta 1. I should not even say alpha and beta. That is just linear combination. Let's remove the alpha beta. So this is the solution corresponding. So this is the solution corresponding to this part. For the other part, you take the same thing but multiplied by x. Right? Why? As I said, in this case, e power ax is e power x sine 2x, e power x cos 2x. Whereas in this case, you cannot choose the same. So you choose x e power x sine 2x, x e power x cos 2x, and that's what I've said here. Okay, so the roots are repeated. So when you choose the way I've said, you have, when you take the linear combination e power x, so this term comes from the first root m1 m3, whereas this term and this term comes from m2 m4. Okay, so this is for the repeated root. Okay, so that's the idea. So let's look at an initial value problem in this case. Okay, so another example where now you are also given the additional. So far you have been finding only general solution. For an initial value problem, you can even compute the constants. Okay, which we have seen even before. We have always been doing one example of a general solution and one example of an initial value problem. So with that practice, let's finish with the initial value problem. So you have a second order ODE. Okay, you have a second order ODE. So you write down the corresponding characteristic equation. You will get a quadratic equation. So you will going to get two roots, right? Complex roots in this case. So the corresponding general solution is e power the real part, which is e power 3x alpha 1 sine 4x cos 4x. So that's the general solution. So it's so second order ODE. So you have a two-dimensional space. So you have a linear combination of two linear independent vectors. So these are the general solutions. Now you use this information that y0 is minus 3 and y prime 0 is minus 1, which is an initial value problem. And using that, you can compute these constants alpha 1 and alpha 2. So if we use, so from y, because we need to use this as well, so we need to compute y prime, to get y prime to be this. Use this information x equal to 0 here and fact that y is minus 3. So minus 3 is equal to, put 0 everywhere where you have x here. So you see e power 0 is 1, which is, and then alpha times sine 0, which is 0, plus alpha 2 cos 0, which is 1. So in this case, you get alpha 2 is minus 3. Similarly, use this information x equal to 0 minus 1. So you get minus 1 equal to 0. 1. Sorry, not 0, 1. Okay, times. So you have sine 4x, which is 0. So this entire thing is 0. Plus cos 0 is 1. So you get 4 alpha 1 plus 3 alpha 2. But alpha 2 is already minus 3. So this is minus 9. Right? And this is 4 alpha 1. And that's equal to minus 1. And from here you actually get alpha 1. What is alpha 1? It is 9 minus 1, 8. So 2. Okay. So alpha 1 is 2, alpha 2 is minus 3. And that's what you get. Alpha 2 is minus 3 and alpha 1 is 2. So you use this information here. You get the particular solution of this initial value problem, which is e power 3x 2 sine 4x minus 3 cos 4x. Okay. So in this lecture, you have studied the way to find all the k linearly independent solutions for a linear homogeneous constant coefficients ODE. See you in the next lecture. Thank you.